Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to continue our discussion on partial differential equations, and in particular the method of separation of variables, which relies on the previous concept that we went over, which is the eigenvalue, boundary value problems, and the concept of superposition and orthogonality to be able to yield a solution for these partial differential equations. So what we're going to do today is just basically an example that extends the applicability of these concepts, in which we will see a combination of different boundary conditions. So let's go right to it. This is modeling methods in ME, and we're going to talk about method of separation of variables, SOV, for the solution of PDEs, partial differential equations. Again, we introduced this method briefly last time, but let's expand on this. So let's go straight to an example. And again, we're going to look at two-dimensional heat conduction, steady, no generation, constant conductivity. This is the same kind of problem that we looked at the other day in the previous lecture. And again, this methodology can be expanded to higher dimensions, three-dimensional problems and so on, but this is just an illustration of how we approach this problem. So again, the equation for heat conduction, remember, when all these conditions apply, we just come down to simply the Laplace of T of x and y is equal to 0, which basically means that the derivative, or the second derivative of t with respect to x squared, and t is a function of x and y, plus the second derivative of t with respect to y squared is equal to 0. That's the Laplace operator of t. So again, this doesn't have to be a heat conduction problem. There are many problems in engineering and science that are governed by this very simple linear equation, namely mass transfer, for example, same equation. For example, hydrostatics, same equation. The pressure is governed by the same equation. In the case of ideal fluid flows, the stream function is governed by the same equation. The potential function is governed by the same equation. So there are many instances in which this equation is valid. It's just easier to illustrate in terms of heat conduction. So in this particular case, let's look at a problem where we have, again, a rectangular domain. And this rectangular domain goes from 0 to L in the x direction, and 0 to lowercase l in the y direction. And internally, well, the domain is governed by the Laplace of t of x and y is equal to 0. There's no time derivative. The temperature doesn't depend on time. This is a steady problem. We already defined that. And let's say that the temperature down here is held at t equals 0. So we have a first kind boundary condition, or fourth or Dirichlet boundary condition on the bottom of the plate. And again, this can be a cross section of a infinitely long column, for example, that's perpendicular to the paper, or it can be a small sliver, L by L, small sliver that is insulated on both top and bottom in the direction perpendicular to the plane. We'll say on this end Q is equal to 0, so that's there's no heat transfer on this side. So basically this section is insulated, and we'll see how do we transform that into a condition that is in reference to T. We're going to say that on the top here, the temperature is equal to some function of x that is prescribed, that is given, some non-homogeneous temperature that is imposed, and a Dirichlet condition. This will turn into a second kind condition, what we call a Neumann condition, remember, or natural condition. And on this side, let's say that we have some convection, okay, some heat transfer is occurring by means of convection, and then H and T infinity, so it's heat transfer coefficient or film coefficient is H, and the temperature of the flow that is convecting energy or absorbing energy from that side is T infinity. Again, these are prescribed values, so I'm going to add the hat here to show that, to denote that those are given. Okay, so let's one thing that's important is to denote that on this wall, let's look at the normal vector and on all the walls, and the normal vector on this wall, that's the wall y equals 0. The normal vector here looks like is 0 in the x direction and -1 in the y direction. So it's pointing down. The normal vector on the top wall here looks like it is 0 in the x direction and +1 in the y direction. So it's just EY. The normal vector here on the right hand side at x equal capital L is equal to 1 in the x direction and 0 in the y direction. And the normal vector here on the left wall at x equals 0 is right here is -1 in the x direction and 0 in the y direction. So that's going to be important in determining what the boundary conditions are, or formulating the boundary conditions in terms of the temperature. Although the one on the bottom and on the top are already formulated in terms of the temperature, so the normal vector will not be necessary. So let's go to the next page to formulate this. So boundary conditions. We already have the governing equation. Now we need the boundary conditions. And what we have is, let's start with the temperature at x equals 0. I'm sorry, at y equals 0. That's on the bottom plate. And that is given as 0. It looks like it's first kind. And it looks like it's homogeneous. All right, so we got that one. The second boundary condition on the top plate, it looks like it is temperature at y equal L is equal to some prescribed function f of x. So it looks like this one is first kind. And we already know how to handle those. We looked at those in the previous lecture. And this one is non-homogeneous. Or homogeneous, as you want to call it. All right, so let's look at the condition on the left-hand side. Right here, we're told that Q, the heat flux, is equal to 0. The normal heat flux in that wall is equal to 0. So normal heat flux at x equals 0 and all values of y is equal to 0. This translates, remember, that Fourier law of heat conduction says that the heat flux is dt is k times the grad of t, and in the normal direction, just we dot it into the normal vector. So this is k dt dn at x equals 0 is equal to 0. Then, furthermore, I'm going to go to the next line. We can say that minus k dt dn is simply minus k dt dx times the normal component of the x component of the normal vector plus dt dy times the y component of the normal vector. All right, and it's equal to 0. We know that this component here, nx, is equal to -1 on the left wall. On the left wall, this component, nx is -1, and this component is 0. So what we basically end up with is k dt dx is at, by the way, all of these is at x equals 0. At x equals 0 is equal to 0. So the final formulation of the boundary condition, I'm going to write it here, is that dt dx at x equals 0, comma y is equal to 0. So I'm going to frame this one. I'm going to frame this one. And I'm going to frame this one. And this is a second kind. Remember, we also call that Neumann or natural condition. And it's homogeneous because it's equal to 0. All right, so let's look at the last boundary condition, which is the boundary condition. Let me bring this up here on the right-hand side. So on the right-hand side, we have convection, which means that the heat flux is proportional to the Newton law of cooling. So this means that the normal heat flux at x equal L happens to be equal to the amount of heat that is being removed according to the heat law of cooling. T at x equal L minus T infinity. And I'm going to use those hats here to denote that those are prescribed values. All right? So that basically means that minus k dt dn at x equal L is equal to h times t at x equal L minus T infinity. And by the way, just to make it simpler, I'm going to say that the temperature of the fluid that is being used for cooling purposes here, which convection can also be used for heating purposes, but in this case, let's assume that we're cooling, so we're saying that this temperature is equal to 0. T infinity is equal to 0. All right? So, then, this will, in turn, be k minus k dt dx and x plus dt dy and y at x equal L is equal to h times t at x equal L minus T infinity. And it turns out that for this particular case, on the right-hand wall, nx is equal to 1 and y is equal to 0. So that's for the normal vector points. And T infinity, we were told that is equal to 0. Okay, so basically this results in minus k dt dx at x equal L is equal to h times t at x equal L. And the other one goes away because we made T infinity equal 0. And this is what happens in this example. So basically what we have is dt dx at L comma y plus h over k times t at L comma y is equal to 0. That is the condition. See, a combination of the slope and the value, or the field variable. And this is called a third kind, and it happens to be also homogeneous because T infinity was given as 0, so this is a homogeneous condition equal to 0. All right, so now we've formulated all the necessary boundary conditions to solve this problem. And now we have a combination of first kind conditions on the bottom and the top, second kind condition on the left, and third kind condition on the right hand side of the domain. So basically, separation of variable applies. So homogeneous GE governing equation, and also only one non-homogeneous boundary condition. So separation of variable can be applied directly to solve this problem. Otherwise, if any of those conditions is not true, then we would have to actually go back and do something to the problem to be able to make it work with separation of variables. So what do? We let as we did last time, the temperature of x and y be equal to some function of x and some function of y. This is an arbitrary decision. But once we plug this into the governing equation, it basically becomes x double prime of x divided by x equals y double prime of y negative divided by y. And then we pick a sign for the separation constant. The left-hand side is a function of x. The right-hand side has to be a function of y. Because it's a function of x and a function of y that cannot be equal to each other, they both have to be equal to a constant. We name that constant lambda square, and we have to pick a sign so that we construct an eigenvalue problem in the homogeneous direction. It looks like the homogeneous direction is the x direction. That's where both homogeneous conditions exist. The y direction, from y equals 0 to y equal L, in that direction we have a non-homogeneous condition. So that's not the homogeneous direction. So in this case, we're going to have to pick the negative sign. All right, so that would generate two separate equations, two separate ODEs. X double prime of x plus lambda square x of x equals 0, and y double prime of y minus lambda square y of y is then equal to 0. So this is an eigenvalue problem, and this is a non-eigenvalue problem. And that's exactly what we want. So let's start with the y direction. We have y double prime of y minus lambda square y of y is equal to 0. And again, that is going to give you a solution, and it's subject to a condition. In the y direction, we can only separate the first boundary condition, as you can see, because the first boundary condition is homogeneous. So the fact that t is equal to 0 means that y at 0 has to be equal to 0. That's x of x, y of 0. Right? So that would just means that y at 0 is equal to 0. That's the only separable condition. So this will lead to y of y is equal to a cosine hyperbolic of lambda y plus b sine hyperbolic of lambda y. And then using the condition, y of 0 is equal to 0, which is a cosine hyperbolic of 0 plus b sine hyperbolic of 0. This is 0, this is 1. That means that a is equal to 0. So we're down to y of y be equal to b sine hyperbolic of lambda y. All right. So what do we have in the x direction? So that's the only condition we can apply. Remember, we have an extra condition that we need to apply, which is a non-homogeneous one, but that one's going to be applied at the end. In the x direction, we have x double prime of x plus lambda square x of x is equal to 0. Let's not break up the boundary conditions yet. We know that the solution of this problem is x of x equals c times the cosine of lambda x plus d times the sine of lambda x. All right. Now let's look at the conditions. The first one says boundary conditions. The first one says dt dx at x equals 0, y is equal to 0. That means that x prime of 0 times y of y has to be equal to 0. And according to the same argument that we used last time, that means that x prime of 0 must be equal to 0. So that's the condition, the first condition that we can apply. The second condition, and I'm going to frame this one, because this is now a separated condition that is applicable to this problem. second condition looks like dt dx at L comma y plus h over k t of L comma y is equal to 0. And if we use the transformation of t into x times y, this would be x prime at L y of y plus h over k x at L y of y should be equal to 0. Then we can take y as a common factor, and that would be y of y times x prime at L plus h over k x at L should be equal to 0. Now, that means also using the same argument that either this is equal to 0 or this is equal to 0. Well, this one cannot be equal to 0 because I will render the entire solution homogeneous. So what we have is then x prime at L plus h over k x at L should then be equal to 0. And that is the boundary condition that we are going to apply. So now we have two boundary conditions to apply to these general solution to be able to find the constants of integration. So the first one says, well, we have x, but we also need x prime. So remember, x prime of x is equal to minus lambda c sine of lambda x plus lambda d cosine of lambda x. Okay, so we took the derivative of the solution. So let's look at the first boundary condition application, which is this one here. So it basically says that x prime at x equals 0, x prime at x equals 0 should be equal to 0, and that should be equal to minus lambda c sine of 0 plus lambda d cosine of 0. The sine of 0 is equal to 0, while the cosine of 0 is equal to 1. That means that d is equal to 0. Okay, so if d is equal to 0, now the solution reduces to x of x is equal to c times the cosine of lambda x. So that's what we have so far. Now we need to apply this condition right here. So if that's the condition, then it basically means that x prime at L plus h over k times x at L should be equal to 0. That's the second condition. And that is equal to the derivative of these, which is minus lambda c sine of lambda L plus h over k c times the cosine of lambda L should be equal to 0. So that's where we are right now. Let me keep this in order. All right. So from here, we can take c as a common factor. So we have c that multiplies minus lambda sine of lambda L plus h over k cosine of lambda L, and that is equal to 0. So again, we have a product of two things. We cannot say that c is equal to, so either c or whatever is in the brackets equal to 0. We cannot say that c is equal to 0 because that will make the entire solution 0. It will make the temperature equal to 0. The whole solution will become trivial. So the only possibility is that these minus lambda sine of lambda L plus h k cosine of lambda L should be equal to 0. And now that one looks like an implicit equation for lambda. So this is an implicit equation for lambda. So what I'm going to do is I'm going to let h over k be equal to big H. We just call it big H. So just to minimize the notation there. So the tangent of lambda L is equal to H over lambda. So that is this implicit relationship for lambda. So the values of lambda that make this equation true, so the roots lambda n of these expression are the eigenvalues. And this right here, as you can see, is the eigenfunction. So these are the eigenvalues, and this is the eigenfunction. So how do we solve that expression? It's an implicit expression, right? So how do we solve a lambda from here? Well, it's just the intersection of these one, or the roots of that equation if we just bring h over lambda to the left-hand side. So graphically, this will simply mean if we plot this, let's see if I can open some space here. This is so the tangent of lambda L will go like this. And this will be an asymptote at exactly pi over 2L. Just assume that this axis is lambda. When lambda is equal to pi over 2L, this is what the tangent of lambda, tangent of this function is the tangent of lambda L, right? Then it will continue like this. So that should have been somewhere in the middle. This continues to be the tangent of lambda L, and this is 3 pi over 2L. Remember, the tangent of x is singular at 90 degrees and 180, so pi over 2 and 3 pi over 2 and so on and so forth. So then it continues like that. By the way, these are all equidistant values. This is 5 pi over 2L. This is the function tangent of lambda L. So this is the left-hand side of that implicit equation. So that function needs to intersect h over lambda. And h over lambda is a function that is basically when lambda is equal to 0, this is infinity, and when lambda is equal to infinity, this is 0. So it would just be an asymptote that would go like this. So this is intersection number 1, intersection number 2, intersection number 3, and this is essentially lambda 1, lambda 2, lambda 3, and as you can see, there's an infinite number of them. They're not equidistant anymore like the eigenvalues that we looked at in previous class, because the eigenvalues were just simply n pi over L, so equidistant by n pi over L. In this case, again, eigenvalues lambda n are expressed implicitly as the roots of tangent of lambda n L is equal to h. And I'm going to put a hat there on h to denote that that's a prescribed value given from the boundary conditions. when there's a third kind boundary condition, then H shows up. And the eigenfunctions are given by x of x is the cosine of lambda n x. And notice that I took out the c, the constant of integration, because it's not necessary. Remember that we're going to combine x with y, and y also has a constant of integration, so the two get blended into one. The more important thing is that it is not just the cosine of lambda x, it's lambda nx, given the fact that lambda n is now an infinite number of terms that make the solution non-trivial, right? So these could also be obtained by querying the table provided on the course site. So basically, there is any problem given like this, where you're solving the Laplace of t that then is broken up into, that has a combination of boundary conditions, right? That then is broken up into an eigenvalue problem and a non-eigenvalue problem. So in some direction you're going to have, or maybe more than one direction, you're going to have an eigenvalue problem. Assume that this is a 3D problem, you might end up with an eigenvalue problem in the first and the second direction, and then the third direction might be the non-homogeneous one. You're going to have to solve an eigenvalue problem, and that eigenvalue problem has a combination of boundary conditions. One that is homogeneous and the other one that is also homogeneous. But you can have 9 possibilities or 9 possible permutations of the types of boundary conditions, right? You can have first kind on the left and first kind on the right. You can have first kind on the left, second kind on the right, first kind on the left, third kind on the right. You can have second kind on the left, third kind on the right, like we have right now. So since we have 3 types of boundary conditions, first, second, and third, you can have 9 possible permutations of possible combinations of boundary conditions on the left and on the right. So, for that matter, I posted a table on the course site. You can open that table directly on Canvas. And this is a table that gives you basically the eigenvalue problem governing equation that applies from 0 to L, right? And the types of combinations of boundary conditions are at x equals 0 and at x equals L. For this particular case, we had case number 4 on the table, right? Case number 4 on the table has a second kind boundary condition on the left and a third kind boundary condition on the right. Notice the H2, right? We call it H, but in this case we call it H2. The eigenfunction x of, and notice that instead of calling the eigenvalues lambda, we call them beta on this table. The eigenfunction is the cosine of beta x, and the eigenvalues are given by this implicit expression, beta m times the tangent of beta ml is equal to H2, or the way we wrote it is the tangent of lambda nl is equal to H divided by lambda n, exactly the same. So the eigenvalues are essentially the roots of that expression right there. And the last one is just the norm. This norm, the inverse of the norm, is essentially the application of orthogonality to these eigenfunction. Is the 1 divided by the integral from 0 to L of the eigenfunction squared. All right, and we're gonna look at that in a minute. So, but the more important thing is that we don't really need to solve any of these eigenvalues problems by hand. All 9 possible combinations are here with the eigenfunctions, the eigenvalues, and the inverse of the norm. All right, so let me bring this up here. So this is what we call case 4. Case 4 on the table. With case 1 case 9, being the one that we solved in the previous lecture, where both sides of the boundary conditions, the homogeneous boundary conditions, are first kind. All right. So this is case 4 on the table. this here, the other entry on the table that we call the norm is basically n of lambda n. Remember, it's the application of orthogonality, which states that the integral from 0 to L of the eigenfunction of lambda n, the eigenfunction n of x times the eigenfunction m of x dx is either equal to 0 if n is different than m, or what we call the norm of lambda n if n is equal to m. All right. So we found, for example, that for the case when the eigenfunction is the sine of lambda nx, when we have first kind boundary condition on the left and on the right, the norm is L over 2. So this integral comes down to L over 2. So in this case, the integral, the norm of lambda n, which is basically the integral from 0 to L of x squared of n of x, so when n is equal to m dx, which is equal to the integral from 0 to L of the cosine square of lambda nx dx, where lambda n is that big, that expression is an implicit solution of that expression, so we cannot show what ln is directly, is given on the table. And in the fourth column on this table, for case number 4, notice that we have the inverse of that norm. Not the norm directly, but the inverse of the norm. And in this particular case, as you can see, the norm of lambda n is equal to L over 2. So I'm actually writing the inverse of these expression right here. So it's L over 2 times lambda n squared plus h squared plus, so L multiplies these, and this is h, and this is divided by 2 lambda n squared plus h squared. So L multiplies only this term in the parentheses. So let me make sure that that's the case. Plus h divided by 2 lambda n squared plus h squared. All right, so that's the correct norm. So why does the table actually give you the inverse of it, 1 divided by it? Because when you're going to be looking at the using the orthogonality principle or property of orthogonality to calculate the constant of integration of the final expression, after you apply the final boundary condition, the non-homogeneous boundary condition, then the norm will appear in the denominator of the final expression, and therefore you need the inverse of that. All right. So let's see. So the final solution that we have so far, so assembling the solution, t of x and y, which is equal to x of x, y of y, which we know now are eigenfunctions, x of n. So there's an infinite combination of them. And instead of just eliminating some or picking one of them, which would not be possible, we combine them all. We linearly combine them all by using the principle of superposition, which says that if one of these solutions of one value of n is a solution of the differential equation, then all of them could be solutions. And technically the sum of all of them combining with some coefficients that we're going to call En are also solutions. The cosine of lambda nx times the sine hyperbolic of lambda ny. So that is a solution that we have so far, such that the lambda n's are given by these expression, these implicit expression. And remember that H bar is the film coefficient or heat transfer coefficient divided by the conductivity. There you go. Now, how do we find the ENs? The coefficients E sub n are found by orthogonality of the eigenfunctions. Again, the way that goes is we're going to apply the non-homogeneous boundary condition that says that the temperature at x comma L is equal to some function f that's prescribed of x that is given, and that is equal to the summation from n equal 1 to infinity of E sub n cosine of lambda n x sine hyperbolic of lambda n L. Right? So now multiply both sides by the eigenfunction. So we have f of x times the cosine of lambda m x, we use another index, is equal to the summation from n equal 1 to infinity of E sub n, the cosine of lambda n x times the cosine of lambda m x. Technically that multiplication goes outside the summation, but we take it in as a common factor. Sine hyperbolic of lambda n L. And now we integrate both sides from 0 to L. Cosine of lambda mx dx is equal to, and I technically should integrate outside the summation, but properties of the integral says the integral of the sum is equal to the sum of the integral, so I am going to just write it inside. E sub n, I'm going to move this sine hyperbolic because it's not a function of x right here, and that times the integral from 0 to L of the cosine of lambda n x cosine of lambda mx dx. All right. So this process will be pretty much done automatically after these examples. I'm not going to go through the entire detailed description of how to do this. This is going to come out automatically. Notice that basically this integral is equal to 0 if n is equal to m, because this function is orthogonal to this function, meaning that at different frequencies they cancel out inside the integral. So when n is equal to m, this becomes the norm. So basically when n is equal to m, it cancels out all the terms in the summation except when n is equal to m. So all infinite terms in the summation are 0 except 1. So basically that goes as integral from 0 to L f of x cosine of lambda mx dx is equal to em sine hyperbolic, by the way this was hyperbolic, of lambda ml times the integral from 0 to L of the cosine square of lambda mx dx. And this whole thing here is the norm of lambda m, which we already found on the previous page. Well, we didn't find it, we looked it up on the table. And see why it would actually, the table will give you the inverse of it because it will go into the denominator of em. So, in order to be clear with the indices, I'm going to switch back from the only index in this expression is m. I'm just going to switch it back to en. So en is equal to the integral from 0 to L of this prescribed function f of x, whatever it is, whatever the temperature on the top plate is, cosine of lambda n x dx. So whatever that temperature is, I can integrate it times the cosine. If it's a constant, for example, it has to be something different than 0, otherwise all conditions are homogeneous, the solution will be 0. So if it's a constant, it's just the integral of the cosine, which is a sine. That's easy to do. Divided by the sine hyperbolic of lambda n L times the norm of lambda n, which we have already identified. So that is the final piece that we needed in the solution. So the solution is this. It's this infinite series, right? Cosine times sine hyperbolic. The eigenvalues are given by this implicit expression, and these constants of integration are given by this expression, where this integral can be solved by hand or numerically, depending on what f of x is. If it's a constant or line or parabola, we can do the separation by integration by parts. And the bottom is the norm that is given by this expression, or just simply 1 divided by the norm, which is directly given on the table. All right. So let me show you now how do we go about implementing this on MathCAD. I've already done it on MathCAD. So I'm going to set up origin to 1 to denote that all arrays would start at position 1, because I am going to be looking for the eigenvalues, or an array of eigenvalues starting at position 1. So I'm going to set L equal to 1, small l equal to 1. I'm going to set the film coefficient equal to 1, the conductivity equal to 1, big H, which is H over K, is obviously equal to 1 divided by 1. And I'm going to set the temperature on the top of this domain, of this rectangular, now square domain, equal to 100. So basically, we have temperature equal to 100 on the top, temperature equal to 0 on the bottom, insulated on the left, flux equal to 0, and some cooling going on the right-hand side through convection with a temperature equal to 0, the convective temperature is equal to 0, and the film coefficient is equal to 1. All right, so I am going to look for the eigenvalues, and I'm going to use this very simple algorithm that I already wrote here for you. I'm going to provide this spreadsheet for you to use, which basically says find an eigenvalue every n minus 1 times pi over L. Remember that when we drew how the eigenvalues will be found, they would actually appear, they're not uniformly distributed, but they appear every pi over L. Essentially, the tangent function, the tangent of lambda n L, would actually be asymptotic or singular every pi over L, or every 2 pi over L, or every pi over L. So what I'm doing is a basic search. I'm looking every I over every 100,000th value of lambda n, and I'm going to look very simply. This is very rudimentary. It's a search that you carry, that every pi over L, you increase the size of x by I over 100,000 pi over L, and then search when tangent of xl, or lambda L, approaches the right-hand side, which is h over lambda. And then I increase the value of I by 1. So basically what I'm doing is I'm searching every 100,000th of that recurring space until the left-hand side and the right-hand side changes sign. When the right-hand side and the left-hand side actually changes, we start by saying the right-hand side is less or is more than the left-hand side. So when the right-hand side is actually less than the left-hand side, it basically means that equality flips sign, and that we actually found the root. The left-hand side and the right-hand side have actually found each other, and at that point, we use x as the next value of lambda n. Okay, and then we return the array lambda, and as you can see, I am looking for the first 25 values, the 25 first values in lambda n. Remember this, there's an infinite number of these, so I can increase this number to 50 if I wanted to. That would just make the whole solution process slower. And if I make that 50, this basically looks for the first 50 eigenvalues. There you are, that array. So I'm going to keep it at 25. I know this series converges very fast. And it converges very fast because these values are these set of boundary conditions are well behaved. Remember, we have the temperature on the bottom equal to 0. The temperature on the top equals to 100. Flux is equal to 0 on the left-hand side. And some cooling through convection on the right-hand side. So we are not going to have any double values at any corner like we had last time, where we had the temperature of 100 on one plate and on the right-hand side we had the temperature equal to 0. So at that corner we had a double value, so the series had a hard time actually converging. Now, the norm, instead of imposing what the norm is directly from the table, I'm going to just say the norm is the integral. So I'm going to let MathCAD calculate this numerically. Is the integral from 0 to L, and the norm is also indexed by n. So if I print norm, it will give me the first 25 values of the norm. And as you can see, they actually tend to converge to a very common value, in this case 0.5, as n grows higher. That's why there's not having too many terms in the series is not necessary. 25 should be enough. The constants of integration E sub n is 1 divided by the norm, the sine hyperbolic of lambda n L. The integral from 0 to L of f of x cosine lambda nx. And even though this integral is very easy to solve, right, because fx is a constant in this case, so it would just be the sine of lambda nx over lambda n times 100. I'm going to let MathCAD do it for me. That's in case I impose something different here and the temperature on the top. And the temperature is just that summation from 1 to n. It's technically from 1 to infinity, but I've truncated the number of terms in the series to 25 in this case, of E sub n cosine of lambda nx, sine hyperbolic of lambda ny. And then I can plot, for example, in this particular plot, I'm plotting the temperature at x equals 0 and the temperature at x equals L. The red line is the temperature at x equals 0, and the blue dotted line is the temperature at x equals L. So on the left hand side and on the right hand side. So as you can see, at y equals 0, the temperature is 0, as expected, obviously, because I'm imposing a temperature of 0 on the bottom. And on the top, at y equals L, y equals 1 in this case, the temperature is equal to 100. It's expected, obviously, because the temperature is imposed at 100 degrees on the top. The left-hand side shows a linear distribution or a linear profile of the temperature, and the right-hand side shows a slightly modified temperature distribution. More importantly, I can construct a two-dimensional array and visualize its temperature as a function of x and y. So that is the bottom plate, temperature equals 0. That is the top plate, temperature equal to 100. That is the left-hand side. As you can see, temperature goes from 0 to 100. The left-hand side is insulated, so all these isotherms, you can see that in the contour plot, all these isotherms have 0 slope when they approach the x equals 0 line. Okay? They approach the slope perpendicular to the contour, perpendicular to the boundary. And on the right-hand side, we have some cooling, so the temperature, the heat flux is being taken out by convection on the right-hand side, and therefore we have this positive slope. That means that the flow is cooling down on the isotherms of a positive slope. So that's it. I'm going to be posting this spreadsheet for you to play with it, and it might be useful for the solution of the next assignment and for the solution of the next exam as well. So thank you for your attention, and I'll see you next class.